So we can do this together like quickly. So yes, the first thing is we have to calculate the reaction, right? So if we do summation of f of x, summation of f of x is equal to 0, there is no other force, so a of x would be equal to 0. If we do summation of, I can do summation of f of y, but what I'm going to do is I'm going to take a moment at point A. Summation of moment at A is equal to 0. So this is 0, this is 0, and we have to calculate the resultant force. So this is the resultant force. This is the resultant force. This force would be 100 into 2, which is 200 Newton. This force would be half into 200 into 2, which is 200 Newton. So both the forces are 200 Newton. Let's draw a free body diagram here. So this is 2 meter, this is 2 meter, and that's the force, which is 200 Newton. This is the force, which is 200 Newton. This distance is 1 meter, 1 meter, and this distance is 2 by third of 2 meter. This distance is 1 by third of 2 meter. So this is going to be 2 by 3, and this is going to be 4 by 3 meter. So we have this AX, AY, BY. So I'm going to take a moment at this point. Summation of moment at A is equal to 0. So if you do summation of moment at A is equal to 0, you will have negative 200 into 1, negative 200 into 1 plus 1 plus 2 by 3, and then you have anti-clockwise force, which is positive 4by is equal to 0. So if you do the maths, by, and also by should be little less and ay should be little more because it's a triangular load, so part of the triangular load will go here, so ay should be more than the by, like intuitively. So if you do the calculation, let me do the calculation. minus 200 into 1 plus 1 plus 2 by 3, and I have to divide by 4. So I'm getting 183.3 Newton. And it should be positive. Yeah. So now we have to calculate AY. So what we can do, we can also do like summation of f of y is equal to 0, summation of forces along y is equal to 0. So you have AY minus 200 minus 200 plus by is equal to 0. So by we already know, which is 183.3 Newton. So if you do the calculation, you will get 216.67 Newton. And the total should sum up to be the total applied forces, which is 400. And now we have to expose the internal forces. So let's expose. So you have this is 100 Newton per meter, this is 200 Newton per meter. Got a section. This is 3 meter, and from the other side you have 1 meter. Oops. And that's the remaining triangular distributed load, and this value would be 100 Newton per meter. And we have already calculated this force, which is 183.3 Newton. So you can either do calculation from here or from here. Either way is okay, but this looks more easy, so we'll do the calculation from this side. So this is a normal force, shear force, bending moment, normal force, shear force, bending moment. So let's use this section. So if we do summation of f of x is equal to 0, we'll get n is equal to 0. And let's simplify this further. So you have I'm gonna draw a resultant force for this. And this is 1 meter. So this should be 2 by 3 meter, and this should be 1 by 3 meter. And the total force is half into 100 into the length, which is 1. So the force is 50 Newton. And we already know this reaction 183.3 Newton. And these are the internal forces. So if you do summation of f of x, you will get normal force. If you do summation of f of y is equal to 0, force, shear force is upward, so positive. This is negative 50. This is positive 183.3 Newton equal to 0. So the shear force will be negative 133.3 Newton. So which means that the direction we have assumed is not the right one. We have to change the direction. If you do summation of moment at, let's just do the summation of moment at this point is equal to 0. I'll call this point C. So let's do this moment at this point is equal to 0. So you have moment clockwise, which is negative m, this one, and then you have clockwise negative 50 into 1 by 3, and then you have anti-clockwise force into 1 is equal to 0. So if you do the maths, you will get the moment. Which is, and we'll go there. So it should be positive 166.67 Newton meter. This is what I'm getting. So I don't know how many of you got like this moment. Not so many. Okay, so I'm gonna just draw. So the final answer. So a of x is 0, a of y is 216.67, b of y is 183.3, this is 0, this is 133, and this is 166, and you can say this moment was clockwise. So this was a clockwise moment, and the force you can put negative, or you can say, yeah. So that's the result I'm looking for. So if you have these values, I think you have done the problem correctly. But if you have other than this, but I think most of you guys have done it right, other than I think moment value maybe. So that's the moment value I'm getting. So there are two ways to draw a final result. So I'm gonna just draw this section, right? So that's the force. This is the reaction, 183.3 Newton. And then the normal force was 0, and the shear force was negative. So, we assume the direction upwards, right? So the answer came out to be negative. So we will change the direction. 133.3 Newton. And the moment came out to be same, positive, so we will not change the direction for the moment. Moment is 166.67 Newton meter. So that, or what you can do is, if you don't want to change the direction, because our shear force came out to be negative. So another thing you can do is you can keep the direction as it is, but put the negative sign. That's the final answer for this. Okay. So we can try to do some exercises. Like I will upload these examples from the workbook. So in the workbook, in the first chapter, we have 3 examples. So we'll try to finish. Otherwise, I will upload in the D2L, and you can see if you have any problem, you can just let me know. But let's just try to do this example. Example 1.1. So it's a 3-dimensional example. So we'll try to calculate the reactions for this case. So this is z-axis, this is x-axis, this is y-axis. So we have to calculate the reactions for this. So let's just draw a free body diagram. This is y-axis, this is x-axis, this is z-axis. There is a force along z direction f of z, and there is a torque along z direction, which is tz. And you will observe 3 reaction forces. So you will have, if I call this point A, you will have A x, you will have A y, and then you will have A z. These are the reaction forces you can see. Like, so these are the axis, x-axis positive upward, y-axis positive outside the plane, z-axis positive this direction. So these are the reaction forces you can see. And also there are moments. So in addition to forces, we also have moments, but I don't have space, so I'm just drawing it here. So I'm going to draw axis first. So this was x-axis. This is x-axis. This is y-axis, and this is z-axis. This is z-axis. This is x-axis. This is y-axis. So you will also have moments along these 3 directions. So you will have along x-axis, I'm going to draw a moment like this. That's the moment which is going to be a resistive moment, which is going to be acting along x-axis. And along y-axis, that's the moment. And along z-axis, that's the moment. So we have to calculate these 3 reaction forces, and we have to calculate the 3 moments. And how we know the direction of the moments from the right-hand rule. So x-axis is positive along the y-axis, so that's the direction of the moment. And so you can see the curl of the fingers is this way for the x-axis, and the thumb is pointing the direction. So this is positive moment because the y-axis is positive along upward direction, and the direction of the moment is also the same. But anyways, we can use equilibrium equations, which is, so it's a 3-dimensional problem. So we will have summation of forces along x-axis is equal to 0, summation of forces along y-axis is equal to 0, and summation of forces along z-axis is equal to 0. And also we'll have moments. summation of moment along x-axis is equal to 0, summation of moment along y-axis is equal to 0, summation of moment along z-axis is equal to 0. So this torque, you can also convert this torque into moment because that's the direction of the torque, right? So if that's the direction, the curl of the finger is actually the moment or a torque. So I'm gonna replace this with a moment. So I mean it's along the z-axis. I think it's the opposite direction. Something like that. Or you can make your life easy, or you can also write this in a different way. That's the force Z, and that's the torque dz. That's the moment along x-axis. That's the moment along z-axis. That's the moment along y-axis. So either you can draw it like this way, or you can draw it like this way. It's like either way is fine. So I'm going to start using equilibrium equation. So if you use summation of forces along x-axis is equal to 0, so x-axis is upward. So how many forces are there along the x-axis? I can only see ax. I cannot see any more force. So ax is equal to 0. If you do summation of forces along y-axis is equal to 0, so which one is the y-axis? So y-axis is outside the plane of the paper. So there is no force which is acting outside, so ay is equal to 0. So we'll do summation of forces along z-axis is equal to 0. So how many forces are, so z-axis is, this direction is z-axis. So how many forces are along the z-axis? There is a z, and also there is fz is equal to 0. So az would be equal to negative of fz. That's what I am getting. We can also do summation of moments. I'm going to do summation of moments at this point, and let's call this point C. Summation of moment at C for x-axis equals 0. So all the moments along x-axis, so how many moments are there along x-axis or moment arms? So you have m of x, and I don't see any other forces acting like upward. Fz is also not going to create a moment arm, and tz is also not. So m of x is equal to 0. If you do summation of moment at C for all the axes along y-axis, so this is y-axis. So you have moment y, and you also have I think that's the moment arm, LC. So you'll have negative f of z into LC is equal to 0. So moment would be f of z LC. That's the moment I'm getting for the y-axis. So y-axis is basically outside the plane. So that's the moment. which is positive because the direction of the axis and the rotation of the moment both are giving me same direction, so I put positive sign. And that's the y-axis. So that's the force, and that's the moment. And if you do summation of moment along z-axis equal to 0, which is this is the z direction. So this is m of z and plus dz. So I am getting this force. So since it's a three-dimensional problem, so right-hand rule makes more sense, but other convention will also work. Is it clear or? So we'll do one more example. We have like 10 minutes and we can do example 1.6 and I'm gonna upload example 1.5 on the portal. All right. So it says consider a floor for a shed that is 16. So that's the dimension of the shed. That's the dimension. This is 16 feet and this is 10 feet 8 inches. It is composed of 9 6-foot long dogless. So these are 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is what is drawn here. And the length is 16 feet. And they are spaced at 16 inches on center to center. So the distance between one sphere and another one is 16 inches. Each joist, so these are the joists, each joist is placed on the concrete footer. These are the footers. So these joists are placed on the concrete footer. So the local building codes require the floor support live load and a dead load. So there are two type of load. So let's on the first. So we're gonna talk about this one joist and this one of the joists. We're gonna try to calculate the total loads on one of the joists. So one of the joist is drawn here. So if I just extract one of the joist and it's located on concrete footer. These are the two concrete footers. So basically it's like placed on top of a concrete footer. So this is a joist. These are concrete footers, this one and this one. And this joist is 16 feet in width. So if you look this joist from the top, that's one of the joists. I'm going to draw this one joist here. So that's one of the joists. And the length is 16 feet, and there's another joist, look here, and there's another joist here, and the distance between these joists, but we're going to focus on this joist. And the distance between them is 16 inches. That's what the problem says. And there is a load. There is a live load, which is 40 pound per feet square. And then there's a dead load, which is 10 pound per feet square. So remember in the last examples, what we were doing was we were I gave you load, what I gave you load in terms of Newton per meter or pound per feet. But in this case, we have pound per feet square. So it's an area, it's not a linear load. So I'm going to draw a load. So the load is 40 pound per feet square and the load is 10 pound per feet square. These are two kind of loads. One, you have a dead load. Dead load means like the table and chair. These kind of loads are called dead load, and the live load are like people moving on to that floor area. That's a live load. So we have to convert. So whenever you are given the loads in pound per feet square, like the bottom is area, you have to convert it to linear. So that's the load which is acting on the top. So we are interested in this joist. So we know half of the load from top will go here, half of the load from the bottom will go here. So that's the tributary area. But you don't have to remember all this. All you need to know is you have to calculate the distributed loads from the dead load and the live load, right? So let's simplify a bit. So that's the joist we are interested in. And we can reasonably assume it's a simply supported beam because it's just placed on top of a footer. So that's what you can assume. And the distance is 16 feet. So basically it's a simply supported beam, this joist. And since it's a simply supported beam, you will have reactions. So if I call this point A, if I call this point B, this is A of X, this is A of Y, this is B of Y. But we need to know the loads. So we know I'm going to draw this like this. So this is a distributed rectangular load. So we have a dead load and we also have a live load. So we have to calculate these dead loads and live loads. The dead load is given as 10 pound per feet square, and live load, the dead load is given as 10 pound per feet square and the live load is given as 40 pound per feet square. But this is feet square, we have to convert it to feet. So we have to multiply by this because we have been given load. So this was 16 feet. And if this is a joist, this distance is 16 inches, which comes out to be 16 by 12 feet. So the load was given in terms of area. Area is 16 feet into 16 by 12 feet. That's the area. And we have been given load in terms of feet square. So we have to convert it to feet. So we have to multiply by 16 inches. So if you multiply by 16 by 12, multiply by 16 by 12, you're going to get the loads which we can work on. So the live load is 50 3.3 pound per feet. So now we have a two-dimensional problem. Before we had a three-dimensional, we converted it to a two-dimensional problem. And similarly, that's so this was a real example, but we tried to simplify because we want to calculate the load on one of the joists. So we just simplified it and we made an idealization for that beam. So finally, that's what we will get. So the total, so we have calculated now the total load. The total load, let's call it W, is live load plus dead load is equal to 53.3 plus 13.3, which comes out to be 66.67 pound per feet. So that's the total load. So 53.33 plus 13.33, you get 66.67, yeah, load. And we know for a simply supported case, these are the reactions. You have By, you have Ay, you have Ax. So now you can calculate the reactions. So if you do summation of f of x is equal to 0, you will get A of x is equal to 0. If you do summation of, if you do take moment along A is equal to 0, you're going to get By. And if you do the calculation, you're going to get 533 pound. And if you do summation of f of y is equal to 0, you're going to get Ay, which is also 533 pound.
I don't know is the result of coursework by 16.
Yeah. I mean, I didn't get your question correctly. So yeah, you have like pound per feet. You can multiply by the length, you will get the total force, and then you do the reaction there. Yeah. And since it's acting just in the middle, I mean, if you calculate the resultant force, what is the resultant force? Resultant force is 66.67 multiplied by 16, right? So the resultant force is 66.67 multiplied by 16. The resultant force is 1066.72. And since this force is acting in the middle, you divide by 2, you'll get Ay and By, which is like half of this. Yeah, from next, we will do chapter 2, like about the stresses and strains and Hooke's law.